here is a graphical view. Part 1. And so when, why is it that this is so nice to be able to solve these? And we can show in 2 dimensions kind of what's happening. And, so I won't make these sketches real perfect or anything like that, but let's just look at, say I have something like maximize z equal x1 plus x2, subject to, let's see, so we'll have our positivity constraints, so I'll put that down here. X1, x2 are greater than or equal to 0. And then let's do a couple of constraints. Let's see, what do I want to do? Maybe something like 2x1 plus x2 has to be less than or equal to 4. And let's just switch it up and do x1 plus 2x2 has to be less than or equal to 4. Now, I can actually, since there are only 2 variables, I can look at a graph of what this is saying. So here's x1, here's x2, and 1, 2, 3, 4. 1, 2, 3, 4. Now, if I start looking at these 2 constraints here, how do I plot this inequality? Well, I do, I would say, that x2 is equal to 4 minus 2x1. I would plot that. And so that is the line that heads down like that. That's not too bad. And then here I would have x2 is equal to 4 minus x1 over 2. And so that is that line. But now the inequality parts. So with the inequality here, this is actually x2 is less than or equal to that, and x2 is less than or equal to that. And so to do, inequalities, I can check inequalities by just checking a single point in these linear inequalities. I can look at 0, 0, for instance, and 0, 0 works in both of these. I'll get a number less than or equal to 4. And so I'm supposed to shade in, everything this way, but the constraints say I have to have both of those constraints true, and I need x1 greater than or equal to 0, so that's out this way. x2 greater than or equal to 0, that's that way. And so what we call our feasible region, all our possible values are in this region. And I'll do a part 2 on decimals where you can see things a little better. But we have that. And then what I'd like to do is maximize x1 plus x2. Well, pick a number, like x1 plus x2 equals 2. Well, that's the same thing as x2 equals 2 minus x1. Oh, that's just a straight line function, y-intercept 2, slope -1. But notice, if I say, well, x1 plus x2 equals 4, then I will have x2 equals 4 minus x1. Notice, same slope, different y-intercept. So these are going to all be, any value that I get from this is going to y-intercept in this particular case, because I'm not dividing anything, but the slope is always -1. And so, what happens is all my possible values for z just make these parallel lines with slope -1, and I want the one that's farthest out, because you can also check that, is this might be something like x1 plus x2 is equal to 5, whereas if I have one in here, that might be x1 plus x2 is equal to 1. And so as I increase my value here, I'm just looking at a line that's moving out that direction. And so as I look at these parallel lines, I want the one that hits that corner point right there. Okay, so graphically that's what's happening. Now I'm going to clean that up a little bit. Is again, graphically in canonical form, what's happening is I'm making a convex feasible region. Okay, convex means that if I have any 2 points in the region, so there's a point, and I draw a line between them, it's still in the region. That's a convex region. So a circle, some convex things, a circle is convex, a square is convex, a star, pretty bad star, but hey, maybe it's supernova or something. That is not convex because, for instance, if I pick those 2 points and then draw a straight line, it goes outside the area. So if I have a convex region made by all these inequalities of linear inequalities, and then I have a linear objective function that I'm trying to maximize, so linear function that I'd like to maximize. I realize now I didn't put that in the video. I don't think the very first video I didn't say objective function, but that what you're trying to maximize or minimize is an objective function. So I'm trying to maximize it. What's going to happen is, because it's a straight line, and I'm either going to be moving it this direction or the other direction, notice it's always going to hit at a corner. And so I should, you would think, be able to find that point. And actually it turns out, relatively speaking, it's pretty easy to find that point. Now, what can happen is, suppose I've got this convex region. I could have an objective that is parallel to one of my constraints, right? And so you would get that. Now notice it still hits at corners, and it also hits a whole bunch of other spots. But to say that it will always hit a corner where it's maximized is true. It may hit more than one corner, but it will always hit at least one corner, typically one corner. But there are cases where it can definitely have more than one solution. Okay, so that's the graphical idea of what's going on. And a lot of the the methods to find this answer either tend to go from corner to corner. So there's a corner, then it goes to that corner, and then it goes to that corner, and says, I have the answer. Or actually they make their way sort of inside and find a corner. Those are called interior point methods. Going from corner to corner is called the simplex method. Okay, and we will probably use the simplex method most of the time. All right, so that's the graphical idea of what's going on. We just make these convex polygons, and we search the corners is pretty much what's happening. But again, we're going to be mostly interested in the modeling aspect.